today we will discuss about this multivariate Gaussian density function. So this is the density function of a random vector x, right? You have the random variables x1, x2, x3 and so on up to this xn. Individually they are Gaussian, right? x1 is Gaussian distributed, x2 is Gaussian distributed and so on up to this xn. They are all the random variables, they are Gaussian distributed. If I want to know what is a joint density function, it means that the density function associated with what? The vector x, right? So if I want to know that, that is what is described by multivariate Gaussian density function, right? So this is the density function for the random vector x, in which the individually x1, x2, x3 and so on, they are all Gaussian. Jointly they are Gaussian. So this is what we call as multivariate Gaussian density function. This is described by the mean vector mu, right? This is a vector actually, and the covariance matrix Cx, right? So if I know the covariance matrix and mu x, you are through, right? So we can cross check for the random variable x what is the result, right? So if n is capital N is just 1, so you get 2 pi power half, that is square root of 2 pi here, and your Cx is simply what? Sigma square, right? It is just a variance. So you get what? Square root of 2 pi sigma square, right? So for the special case when n equal to 1, we get this e power minus half. X is a variable now, I mean it is a single element, x minus mu x, it's of size 1 cross 1, right? So x minus mu x, right, the whole square will come because here one more x minus mu x is there, and your covariance matrix is no more matrix, it is just a scalar, so I can bring it down, right? It is sigma x square. So this is the classical, right, single variable, right, Gaussian density function, which we already know. For the multivariate Gaussian density function, we need covariance matrix and mean vector mu x, right? So if I have mu x, you know, that is described like this: expectation of x1, it goes like this, and then expectation of xn. This is what the vector mu x indicate. And if I want to know about this covariance matrix, x minus mu x is transpose here, because here this vector size, and this is n cross 1 and this is 1 cross n, and the size of the covariance matrix is going to be n cross n here, right? Expectation of x minus mu x into x minus mu x the whole transpose, but here it is other way around. X minus mu x transpose will come first, because that is going to be end up with what? The scalar, because this is 1 cross n here, n cross n, and this is n cross 1, so it ends up with what? 1 cross 1, the scalar there. But here this covariance matrix ends up with what? The matrix here, which is of size n cross n in this, right? So this is this multivariate Gaussian density function. There are interesting properties for this Gaussian density function. As I told you earlier, individually they are Gaussian, x1, x2, x3 and so on up to this xn, they are Gaussian. If I take two random variables instead of one by one, right, let us, if I take x1 and x2 alone, if I see what is that distribution, that is also going to be Gaussian. And in fact, the conditional density function, that is also going to be Gaussian. Conditional density function means if I divide this vector into two parts, right? So let me explain this one with one application. So this is basically estimate theta, but this time this theta is not a random variable, it is going to be the random vector, right? You need to estimate this theta based on what you observe, right? Section. So it's like, you know, multi-input, multi-output model. Here we have, like, you know, theta 1, theta 2, this theta n, and in the receiver section you have like this y1, y2 and so on up to this ym, and you have the channel. This is the channel characteristics here. So I have drawn only few connections, but the idea is, right, so every theta in the transmitter, right, it is connected with every y in the receiver. It is connected with a line I have given. That line indicate it is a channel characteristics. If it is a flat fading, that is described by what? Single variable. Right. So if I assume that it is a flat fading, right, so you are going to have this one with H11 and this connection is going to be what? H&M. Remember that this is this multiple input, multiple output structure here. You are transmitting N in the transmitter. In the receiver you are receiving M. So you can have redundant antenna. Right, so you may wonder why M, only N you are transmitting. You can even have only N antennas in the receiver, yes, but we choose M greater than N also, just to keep what? Redundant, so that the estimation may be better. We get this N values, you know, to estimate. We get the additional information about this channel characteristics. If one of the link is, you know, is very worse than other link may help, right? I mean, this is just the intuitive idea, but the basic idea is if I add, you know, redundant antennas to the receiver section, again intuitively we understand that the estimation may be better, right? So that is what we need. So here in the receiver section, what we really get is not only y, that's an interesting point, you already know that it gets added with what? The noise also. Here this model is going to be like this: y equal to h theta plus n. N is a noise and h is a channel matrix. This is a simple model, and this channel matrix H, this is n cross 1, so this is m cross n here, and this is m cross 1, and this is m cross 1, right? Now in general m is always, you know, we choose it as greater than n, we use receiver section so that the estimation may be better. It is like that, right? So as usual, we are interested in knowing, right? We know how to do this estimation. Major ways of doing that. One is minimum mean square estimation, right? And you have MMAE, minimum, right, mean absolute estimation, and then we have this map, right? So in all the cases, what is the posterior density function. Here we actually talk with what about this theta vector to be estimated. So here the prior is f of theta here, and this is going to be your posterior, and this is going to be your likelihood. But we are interested in knowing this. That is what I am talking about, this particular multivariate Gaussian density function. Here we are talking about the density function, conditional density function of theta given y, right? If this theta vector associated with the transmitter, we are not how that is distributed, right? And if we assume theta is Gaussian distributed, this is just the assumption. If theta is Gaussian distributed, then the function f theta given y is also Gaussian distributed, Gaussian density function. It is a multivariate Gaussian density function here. So this is if theta is Gaussian distributed, then f of theta given y is also Gaussian distributed. It is interesting to note, I think we have already discussed that, I just want to recollect that, if the posterior density function is Gaussian, what is that estimate about? Estimate is simply its mean, isn't it? Its mean itself is that estimated. In fact, all the three estimate coincides. Answer you get, right? If the posterior density function is Gaussian, mean is same as that of what? Median is same as that of mode. So once if I know that it is Gaussian distributed, then it is enough for me to know what is that mean. That's it. The density function f theta given y is Gaussian distributed, and we would like to know what is that mean. I already told you that it is Gaussian distributed. That is what I told, that conditional density function is also Gaussian distributed, right? So let us see what is that covariance matrix for this. Then so let me write here cy, and that's cy theta here, and this is c theta y, and this is c theta. What I am doing here is I am formulating a vector with y1, y2 and so on up to this ym, and then followed by theta 1, theta 2 and so on up to this theta n. Basically I am formatting a new vector y followed by theta, so that the size of that vector is m plus n, right? So theta followed by y here. So the covariance matrix of this, this is if I call this as something like z here, and this is going to be your cz. The covariance matrix of the random vector z, right? We have 4 matrices in that, right? These are all matrices actually. This is the covariance matrix here. This is of size m cross m here, and this is m cross n, and this is n cross m, and this is n cross n, and hence this size is n plus m cross n plus m. It is like this. So you are getting this covariance matrix CZ of this form. So if this is the case, the Gaussian distributed, right, f theta given y, this is Gaussian. So the moment when it is Gaussian, it is described by mean vector, right, and then matrix. The mean vector is given by mu theta plus, you have to see to this matrix here, theta y, C y inverse, y minus mu y. Here that size is n cross 1, C theta y it is n cross m, and C y it is m cross m, and this is m cross 1, right. So this is n cross 1, like this, and here this is C theta minus C theta y, C y inverse, C y theta. Writing the result, right. So basically what I am trying to say here is posterior density function theta given y equal to y, right, that is also Gaussian. It means that is described by two parameters. One is the mean vector, another one is covariance matrix. That's what I have written that expression here. And what we are interested is only this for this particular task. For this case, we are interested in finding out this mean. I mean, just for the sake of completion, and you must know the result, and that's what I am writing this covariance matrix of the density function theta given y equal to y. But as far as this problem is considered, we are interested only on the mean vector, not the covariance matrix. The mean vector itself is the solution. That itself is an estimate. So the estimate here based on that observation of y, if I want to know what is that theta in the transmitter, right, so that is given as theta cap. I call it as theta cap here, is an estimate. In fact, this theta cap estimate, it is a vector of course, for FMSE, MMAE and MAP all are same, right, all are identical, and that value is mu theta plus C theta y, Cy inverse mu y, right. This is actually the solution, but we will simplify this because we can find out theta y in terms of n, because we have this noise information which we assume now is white here. This is a white noise. There is a reason this y is also becoming what? The white means what? The covariance matrix is a diagonal matrix, right, that is called white, right. If it is a random variable, is what? Impulse, and the spectral density is flat, right. If it is a random variable, we can identify the white noise if its autocorrelation is impulse and spectral density is just flat, right. We can, for the multivariate, right, more than one variable, if it is a random vector, we can identify that the random vector is going to be what? White, right. Covariance matrix. If the covariance matrix is diagonal matrix, we say that it is a white. Formally we are going to start the random process from tomorrow, right. That time I will explain you why it is so, right. But right now I am just giving you the result, right. So if the covariance matrix Cn happens to be sigma n square and so on, this one, and this side it is going to be 0. So the matrix n is of size m cross m. Here also it is going to be m cross m in this. It can be written in this way also, sigma n squared I. I is the identity matrix. Sigma n squared is that noise power, right? So that noise, what we have considered this n is white if its covariance matrix Cn is diagonal with the diagonal elements sigma n squared here, right? So this is the point. I wanted to use this fact in this so that I can get a simplified version of this. So we will start with C theta y. So what is this basically? This is theta minus, and this is going to be your column vector, right, which is of size. What is the size here? Because theta is n, right, n cross 1, and you have here y minus mu y, the transpose in this. This is 1 cross m, right? So this is having the size n cross m in fact. So that is what this covariance matrix in this. It is not for the same random vector, it is for two different random vector we are chosen, theta and y, and that's what we get like this, right? So if I expand that, you get the first term, second term, third, mu I transpose here. You get 4 terms in this. So this one we can keep as it is, theta and y transpose. And here case, you have this mu y which is constant here, so that I can take outside. So expectation of theta is going to be what? Mu theta. So I'll write like this, mu theta mu y transpose, like this. Minus here mu theta is constant, that I can take outside. Expectation of y transpose, it is mu y transpose here. And similarly here both are constant, so I can write it as mu theta mu y transpose. Expectation vanishes in this case, and this two gets cancelled. You get this expression like this, but still I can simplify. In place of y, I am going to use h theta plus n, because I want to use the characteristics of the noise in this, and of course I can is at mu y transpose also. Y is h theta plus n. So if I take expectation on both sides, like this, right? So what is that you get? This is h is constant, so I put it as h here, and expectation of theta, it is mu theta. N is mean of the noise. If we assume that it is 0, right? So it is going to be what? 0 vector. So I take this h mu theta in place of this mu I transpose here. So h mu theta, the transpose, right? So this is equal to here expectation of theta transpose here, and you get this is h transpose plus expectation of theta n transpose, and then minus mu theta transpose and h transpose here, right? Expectation of theta n transpose. Theta is vector, always you have to understand that, right? So this is n cross 1, and this is 1 cross, what is the size of n? It is m, right? This is n cross m. So it is of size here, right? But every element in that matrix, for example, if I take 1 comma 1, what are the two elements you get? Theta 1 and n1, isn't it? Are you getting this point, right? So this is nothing but a matrix. It's nothing but a matrix in which this first element is going to be an expectation of theta 1 n1, and this one is expectation of theta 1 n2. It goes in this way, right? So like that, that is the meaning of it, right? So because what is it? Vector is what? Theta 1, theta 2, theta 3 and so on, and this is n1, n2, n3, and I take the multiplication theta 1 n1, theta 1 n2 and so on, and take the expectation over that. So expectation over the individual elements. I hope this is clear to you, right? Right? So now, but this theta and n, what are those things? Theta is the random variable associated with what you transmit, and noise is what? The additional thing what is added, right, at the end, finally, h theta plus n. So this theta and n is assumed as independent. This is another point, right? They are assumed as independent random vectors. So it means that the variable is also what? It is going to be independent. If that is the case, I write here expectation of theta 1 into expectation of n1. So expectation of n1 becomes 0. It means that the whole matrix is actually becoming 0. It means that this will again vanish, right? So now here expectation of theta, theta cap, I mean theta transpose, and h transpose, which is basically the constant. H is a channel matrix, and in this case I told that there is a way to estimate the channel characteristics. The third case, right, we modeled that channel as the Rayleigh-Ritchian, and the third case we estimated the channel characteristics, right? So this is of the third case. It means that I know what is my channel matrix H. With that assumption only we are actually discussing this topic, right? H is known. H is known, right? The matrix H is already described, and we already know what is that H matrix. So if that is the case, H is constant, so I can take this one out. So you get expectation of theta, theta transpose, H transpose is there, expectation of theta, theta transpose minus mu theta transpose. It is nothing but what? It is that covariance matrix of the random vector theta itself, multiplied with what? H transpose. So this is equal to C theta H transpose, right? So we got an expression for C theta y. I will find out for Cy also, the same fashion. So Cy is expectation of YY transpose minus mu y transpose, right? So we already know that Y is what? H theta plus n. We can use that expression here. Right? So H is constant, that I told you, because we are having the channel matrix fixed. H is known, right? If that is the case, this first term, this H will come outside, and I get theta transpose, and this H transpose will come outside, and coming to this product, right? And if I do this product here, Yes. Put it as expectation here. Thanks. Right. So the first term here, what is that you get? H theta, theta transpose, H transpose, that you get. And then expectation of H theta n, 0, because theta and n are independent, so that becomes 0 here. Similarly n H theta, that is also going to be 0, and you get the term expectation of n transpose, that will be there. But here you need to take this expectation and then we need to take this product. It means that mu y is basically H into mu theta. Theta plus mu n is already 0. So mu y transpose, so you get what? H mu theta transpose, H transpose here, right? So I want to combine this with the last one, so you get H expectation of theta transpose minus mu theta transpose. It is nothing but c theta, right? This is c theta here, H transpose, and we know that expectation of n transpose, it is sigma n squared I, right? So this also we got the result, and we can finally write the result there. So theta cap, I will write it as this is MMSC, MMAE, and as well as map. And you are going to estimate based on the observation of y. So that is given as what? Mu theta plus c theta y we derived here, that is c theta H transpose, and then cy here we have here H c theta H transpose plus sigma n square I, the whole inverse, and then finally you have this y minus mu y, it is H mu theta estimate. You see that? How can I estimate what is being transmitted from the transmitter? Based on the observation of y. The moment you receive y, I can substitute in this expression, I put it in this y, and I can get the result for theta. Provided, what is more important here is, we had a wild assumption that theta is what? Gaussian distributed. So if theta is not Gaussian distributed, we will not get this expression. In fact, if theta is Gaussian distributed, I mean whatever we transmit from the transmitter, that should also be the Gaussian distributed. So, but it is in your control. Theta is in your control. Transmit is in your control. You can make that theta to be the Gaussian distributed, a proper choice. If we do, type of modulation, the technique what we use, this theta, if it is Gaussian distributed, we have a very straightforward equation, isn't it? So which is mu theta, which is the mean of the random vector, which you must know. C theta, the covariance matrix of the random vector associated with the transmitter, that you must know. Is known, it must be known, H, assuming that it is a flat, and you must know what is that H. And then if I observe y, then straight away I can find out what is that theta. Point, right? So here E and map, right? In all the cases the solution is going to be the same, but only problem here, it is this inverse. Problem in the sense, in reality finding out this inverse is slightly complicated, because you know what is the size of this H. What is the size? Y, I think I have, what is the size of Y I assume? I erase that. N cross 1. Y in the receiver section, which is M, right? So it is Y is M cross 1. So, I'm sorry. Then H is M cross N. Isn't it? You see that H is M cross N, and that is the size here. If M is, in fact, we use M to be very large. M cross N here, and this needs to be N cross N here. This is N cross M here, and N is also this M cross M here. So this matrix where you are trying to find out this inverse, that matrix size is what? M cross M. Use, in fact, M is greater than N. What we receive in the receiver section is going to be greater than N, and if I use more number of antennas in the receiver, the matrix size is going to be bigger, and finding out that inverse is complicated. It is not just like that. I am telling it is a real problem. In taking inverse, right, is a problem actually. Because that is not that much easy in real time to find out that inverse, right? If you think about the classical method, right, it's difficult. We need to some alternative way of finding out this inverse, right? And we can go for this matrix identity of finding out this inverse in a different way. It is possible, right? I give this as a task for you. It's such search and tell me, right? I want this to be done, but exactly the same answer you are going to get, right? But using this matrix identity, right? Like, what is that structure you need? You need something like this, see the whole inverse. The equivalent expression for that, right? Replace that expression here. Comparatively, right, the matrix size which you wanted to take that inverse, that is going to come down. So that I am giving it as a task. It is there, right? I don't want to tell now. So that is another way of writing the same expression, right? Replacing that inverse with another form, right? Okay, well, we assume this theta is what? Gaussian distributed. That is very important. If it is not Gaussian distributed, about it, right? We don't know what distribution is theta, right? So if it is Gaussian, then only we can go for any of these techniques, right? So, but you know that whether it is Gaussian or not, right? That is the case. If you don't know this prior, if you don't know that posterior density function, there is another technique other than this, MMSE, MMAE map. What is that? It is maximum likelihood estimation. In that case, you would like to know the estimation of what? Theta given y, it is the posterior density function. Y given theta is going to be your likelihood function, right? So in that case of likelihood function, right, y equal to h theta plus n. So what is the nature of y? Individually, what is that y given theta? Because theta is given h theta. Your condition on theta, that's what we mean. You see, for example, let us say y1. What is the expression for y1? The first row of h multiplied with what? All the theta, right? Theta 1, theta 2, theta 3 and so on. I said that theta is fixed. It's a linear combination of what? This theta is happening, and I told that you are fixing it up what? Theta. But in that case, this first term h theta together is going to be some constant, some fixed value. But what is more important is the second term. It's a noise. N1. First row getting multiplied with what? All theta, that is becoming fixed because you are fixing it up what? Some theta. Right? So the n is what? n means you are taking that first element n1, which is Gaussian distributed. In that case, what do you think about the density function of y1? It is going to be Gaussian, right? So theta given y is crucial. That theta is what? Gaussian distributed. But here, safer side, by if I fix this theta, then we are able to understand that y is Gaussian, right? So we can go for this maximum likelihood estimation. We need what? Fy given theta. Then we can go for what? Maximum likelihood estimation. Yeah, that is what also being used. If we don't know that, if you are not very sure that theta is Gaussian distributed, or if you are not able to make that theta is Gaussian distributed, because it is in your control. What you transmit is in your control. If you are making them as Gaussian distributed, fine. We can go for a proper estimate like this, right? But if it is not, then we have to go for maximum likelihood estimation. Maximum likelihood estimation, we would like to know what is that likelihood function of what? Y given theta, which is Gaussian, I already told. But if it is a Gaussian, it is a multivariate Gaussian density function. So in that case, you need to know what is that mean vector and covariance matrix, which actually we got it. We know what is that mean, right? But given theta, theta is fixed. H into theta, given theta. Given theta means I am telling that I am not writing it as what? H mu theta. No. I am writing simply H theta because theta is fixed. Friends. Right? The uppercase theta, I am finding out one particular outcome, theta, right? So it means that expectation of n is 0. Expectation of constant is the constant, which is nothing but h theta, not h mu theta. I am finding out the Gaussian density function of y given theta. That's very, very important. I am not finding out Gaussian density function of y alone. Gaussian density function of y given theta. That's given theta is more important. Given theta. Right? So what about this covariance matrix? The same way we can find out this covariance matrix for y given theta. So it is like, constant plus n is coming, h theta plus n, right? Into what? H theta plus n, the whole transpose, right? Multiply all the terms, isn't it? Having theta and n, theta is anyhow constant, expectation of n everywhere it is going to be what? 0, that vanishes. You get a term called expectation of n transpose, right? Which is sigma n square I. Here is, you know what is that density function. Once you write the density function expression, you would like to what? Maximize, isn't it? So you have to find out the solution for maximizes this function, whatever we get a function. Multivariate Gaussian density function I have already written. 1 by 2 pi power what? N by 2 Cx power of e power minus of x minus mu x, right? Transpose Cx inverse x minus mu x. So in this case you have to write the multivariate structure for y given theta. It is described by its covariance matrix and mean vector. Both are known. So you can find out that. Then I want to maximize that function. Whatever is there in that left, right, 1 by root of 2 pi power n by 2, all those things are going to be constant. We have the term e power minus half, that portion is what having that random variable, which you would like to what? Gives you that maximization or minimization. Maximize that, right? Maximizing this function is same as that of what? Taking log and then taking the maximization. Logarithm is the increasing function. So whatever is there in that power, that will come here, minus of, and ln e is 1. Isn't it? The first term is going to be constant. We get what? Minus of, right? I am saying it is x, but it is not x. I am just saying minus of x minus mu x, the whole transpose cx inverse x minus mu x. That is what you are trying to maximize with minus sign. What? Put plus and try to minimize this. So if I solve that, whatever the solution you get for this y, that is going to be that maximum likelihood estimation. That I am not doing. I am just saying orally. If time permits, tomorrow we will start with that and we will continue with this random process. We will stop here. The main objective here is I wanted to introduce this Gaussian, multivariate Gaussian density function and this usage. Right, in telecommunication, there are many places where we are using that, but most important is your MIMO, multi-input, multi-output model. How many of you are aware of this MIMO technique? Okay, you have to study, right, in your telecommunication. MIMO we are using in your mobile, right? 5G, I mean 4G, and then 5G is also you are having something called massive MIMO. Still huge. MIMO we are using now, and 5G they are moving towards massive MIMO. MIMO is very important, where we use multiple antennas in both transmitter as well as this receiver. This is just the starting point of understanding what is MIMO, right? So the channel link is described by a single element because we are assuming that it is a flat, otherwise it's different, right? We'll stop here, we'll continue the next.